I will now summarize. Due to the presence of the root 2 spin, the locality assumption in deriving Bell's inequalities is intact. The subquantum theory presented here is both local and realistic, providing an interpretation of all known coincidence experiments. Entanglement becomes a property of quantum theory, but not of nature. A single subquantum spin has two-dimensional structure rather than the point particle description of quantum mechanics. As I mentioned before, a fundamental difference between quantum mechanics and the subquantum theory follows from the coherence or interference between eigenstates. This is not possible in the formulation of quantum mechanics because Hermitian operators can only have orthogonal eigenstates. Therefore, there is no interference between them. In contrast, non-Hermitian states have non-orthogonal eigenstates, and hence they can interfere. The sort of coherence between two non-orthogonal spin states gives a non-Hermitian state that I'm discussing. Here we have the Z state taking the outer product with the X state, which gives a non-Hermitian state operator. Neither quantum field theory nor the Dirac equation can predict the exchange spin state. To include the subquantum theory in quantum field theory, it is necessary to extend it to state operators rather than remaining at the level of state vectors. A local realistic subquantum theory accounts for the main features of the experimental data and resolves the anomalies. It predicts a new exchange spin state, and the Bell states disentangle. But more experimental data is needed on such coincidences and biparticles in order to quantify this new state of spin. In those experiments, it is not necessary to be concerned about the locality or the detection loopholes. So what lies beyond? What are some of the consequences of this approach, which appears to complete quantum mechanics? One can only speculate, and so my final comments are simply ideas that arise as interesting notions pop up along the way, and might fit. I have not delved into these, and my list is incomplete. First, quite prosaically, the 1935 paper of EPR can be exonerated, and we can conclude that the objective reality of position and momentum is resolved, since now non-locality can be put into its rightful place in history, like cold fusion. Completing quantum mechanics with respect to spin has led to a number of new properties and concepts that could lead to the resolution of difficulties with modern physics. Spin is ubiquitous and occurs in many particles. It is a fundamental intrinsic property of matter and of many individual nuclear particles. Of course, when spin is in the presence of a probe or other interactions, it obeys the statistical results of quantum mechanics. But in free flight between collisions, a spin goes into its resonant state of zero angular momentum. What is the consequence of that? We have shown that the coincident probabilities are indeed sensitive to the two-dimensional spin structure, as seen from the filtering settings at 45 degrees apart. Could this mean we have to reconsider collisions and Feynman diagrams? What about the standard model? What about other experiments, like the 0.07 anomaly noticed in ballistic electron experiments? 0.7 is the inverse of the square root of 2. How does symmetry breaking and non-Hermitian states affect the formulation? Could the existence of distinct subensembles have an impact on the dark matter problem? What about the cosmological constant? How do we formulate quantum field theory in terms of Hilbert-Schmidt space, and what will be the consequences? Will this affect string theory? There is another point. As enthusiastic as I am about high-energy physics that require huge investments to build instruments like the Large Hadron Collider, it seems that some answers also lie in the low-energy limit that can be done in a small lab with some good optical equipment. Biparticles need much more work. In the subquantum domain, resonance, indistinguishability, and most of all objective reality play dominant roles. There are many more issues that need to be reconsidered, but what is most striking is the totally different conceptual approach that is needed in physics, which comes under the truism, he does not roll dice.